Hello and welcome to this SMT webinar, which discusses some of the aspects of the modelling and analysis of EVs. Now, we are taking questions throughout the webinar today, so please feel free to put any questions into the GoToWebinar pane. If I can, I'll answer them during the webinar. If not, I will stick on the line at the end of the session and answer them then, or maybe send some emails out later on as well if there's any additional queries. So as I say, EVs are obviously a very large topic right now. We're going to try and cover a few aspects of modelling and analysis of EVs which come up quite regularly. So hopefully you've all seen the agenda and the sort of things we're going to discuss. So we're going to look at some aspects of modelling the actual motor itself and how we put in the motor excitation. We'll take a look at doing some flexible mounting points and how we would put those into our models. Have a look at some of the MVH results available when you're using electric motor excitations. Look at some of the minor things we might need to put into our models to get some kind of correlation. And we'll take a brief look at park lock modelling as well, which is a topic that's come up a few times recently. So I want to start off just by talking about the modelling of the stator. So this is really how we would actually bring a motor into our MASTA model. And I've got one of our example models open here that will hopefully demonstrate to you what I mean by this. So we have our transmission sat on the front of our model here. However, we also have, coming out of the back, we have the rotor of the electric motor, and we actually have the motor housing in here as well. Now you will notice, and hopefully it's clear enough on the screens in which you're viewing, that along with the actual motor housing, we do actually have the stator teeth within the model as well. Now this is critical if we want to actually bring in some motor excitations to use in the MVH analysis, because we need to actually be able to connect those or create some condensation nodes on the MASTA model, and I'll demonstrate this in a moment. Now a few things to actually keep in mind when you're bringing the stator model into the MASTA model. So the first thing to note is that it is somewhat of a simplification. So let's just see if I can slice this slightly just to make it a bit clearer. Okay, so hopefully that helps a little bit. So you see there that I do have the teeth in there. However, it is missing a lot of the components, such as the windings around each of the teeth. And therefore you're going to be missing some of the masses, you're going to be missing some of the stiffness. Now it's up to you how you model this, but remember you do have to be able to make a stiffness matrix out of the components that you bring into MASTA. So this is the method we normally use. We just go with the teeth, and we're going to connect to those, input our excitation to those teeth. However, do be aware that if you start looking at your MVH results and you start seeing some modes related directly to these teeth, in which you're getting some excitation, just take those with a pinch of salt, as the frequency in which they're occurring may not be completely accurate, depending on the way you've decided to model. Just be fully aware of the method you've used to model and the kind of things you've chosen to do. So I'm going to briefly go through the process of how we would actually set this model up to use excitations for an electric motor. So the first thing I need to do, so I'm going to go to my design mode, and you'll notice, and you'll see this in most of the MASTA models that you create, whenever you create a power load on your model, it's going to be a very basic setup. So it's going to be a simple icon that we see with the power load, and then down in the properties list over on the left hand side, you'll notice that under power load type, by default you'll get an option in here which just says basic. Now I've got a few different options here. Most of those are related directly to the multi-body dynamics package that we have, which is driver. However, the two that we're going to be bothered with in MASTA itself is basic and electric machine. So the difference between these isn't major. The only change really, if we change from basic to electric machine, is that it's no longer looking for any kind of upstream inertia, because it knows that the motor or the rotor is the end of the system. And we also get some properties down in the properties list here, which are basically asking us to define some of the basic geometry of the actual stator itself. Now at this point, these inputs are quite simple. It's saying that we want to put in a default effective length of the stator teeth, so the actual length of the stator teeth, the inner diameter of the teeth, and the number of slots which we are concerned with. Now this is basically going to control the search regions when we start looking at the FE that we've brought in. So these are somewhat customizable later on as well. But it's a good idea to put some values in here now just to get some feel for where that search region for those condensation nodes is going to be. So once we've changed this to electric machine, if I go back to my imported FE now, so what we'll see when we have a basic power load selected is that when we actually look at our node model for our system, it's just going to have one node in the middle of this power load, and that's where the load is going to go into the system. When we have it set to electric machine, it's essentially going to use that search region that we've defined, and it's actually going to try and create condensation nodes which connect to those stator teeth, and which then allow us to apply load to those stator teeth to actually input the excitation into the system. Okay, so if I move from my import to export tab, you can see I've already brought my housing into my model and most things are already connected up. So the bearings, for example, I've changed my model here from basic to electric motor, as I mentioned. And now when I go into create my connections, so within the connections tab and then create nodes, you'll see now, if I hide some of those components, that it's actually going to make a condensation node at each of those stator tooth points. So you can see there's a lot of connection nodes there by default. However, I can look at these in a little bit of a different way just to make them a bit more visible. So if I go to my input power load, we can see by default it's just going to be looking for one whole ring for those, which is going to create. However, I can switch in my linked node source to be a flexible node ring, which is then going to use that search region that I defined. So flexible node ring, you can see now that using the geometry I've predefined, it says, or it's saying that I want to use 24 teeth. I've defined a length, I've defined a radius, and it's found some appropriate search regions. Now, there's a chance it's not going to find these precisely. However, we can modify the search region if we wish. If we go over to the search regions tab, we've got full control over the specifications of that search region to make them actually fit nicer with our stator teeth. So if I just modify a few of my visualization options here, just to make sure that we're happy with what it's selected. So I can see by default, and hopefully that's clear enough, that the search region has only been able to find one line of nodes through the center there. So you're going to want to be careful of things like this. That might not be quite the resolution of connections that we want for these kind of things. So this is where we'd have to try and modify the search region. So I can say, for example, we'll try and make this a little bit easier to view. Like so. Okay, so I can modify this search region to make sure that my search is the entire area of the tooth, and then we should get much more nodes being selected. So I can say, for example, that I want my search length to be longer than 200. I want to make sure that I don't intersect any other components. And then I have my span of patch, for example, to make sure I've got the entire tooth selected. Okay, and I can see there that it's actually getting a lot more nodes. It's actually getting the ones that are on the edge as well. And we've got a much greater selection of nodes on each of those. You do want to be careful as well about the type of connections it's doing here. So again, this is kind of personal preference based on what you think your model should be doing. However, when you look at your input power load, you want to make sure that you've selected the correct choice between kinematic and distributing connections. So this will apply to every one of those contact regions on here. So kinematic is an RB2 node. So every one of those things there will be stiff, or those connected nodes will be stiff. Or we have distributing, which is RB3, which will make those flexible. Okay, and that's basically our nodes created at this point. So we obviously would have to go through and actually reduce our stiffness matrix, but to save time on this particular webinar, I'm just going to jump to a more completed model. However, the next thing I want to show you is the actual import of the electric machine data once we have those condensation nodes in place. So if I switch to another model, so you see there I have all my condensation nodes, I have all of my connected FE nodes to those condensation nodes. And then if I go to my electric machine data tab, I have the ability to put in some excitation data for the electric machine. Now the format in which we need these varies slightly. So what I'm going to show you today is importing these via an Excel sheet, which is the main format that we use. However, do be aware as well that we have the ability to import JMAG formats and MotorCAD formats as well, if you use those particular pieces of software. So the format of data in terms of Excel, I have two sheets loaded up here. One, these are very much sample sheets, so they're not very realistic excitations, unfortunately, but they'll portray what we're trying to get across anyway. I have a sheet which is showing my tangential loads on the tooth, and a sheet which is showing the radial loads on the tooth. And these are quite simple formats, really. So the first thing we need is a sheet within the Excel document which actually shows the speeds that we are trying to import. So we'll have a number of sheets across the bottom with more detailed information for each speed, and then we put a sheet of speeds which has those individual values in. And what this means is that it will have these values, and then if you actually define a speed which is in the middle of these, it will interpolate between the two. So you are going to be able to analyze any speed, not just the ones in here. However, the more speeds you can get results for, the greater accuracy this is going to be. And it's also worth noting as well that you can have as many speeds as you want. The procedure for importing this information will not change, and it's always going to be the same amount of effort. So if it's easier for you to get more speeds in there, definitely worth doing so. So that's our sheet of speeds. And then if I go forward onto my actual data sets, so this one is the tangential loads on each of the teeth. You'll see in my first row up here, I've got a very simple ID number, and this is simply the ID of the stator tooth that I'm looking at. So you see that I've got 24 stator teeth in this case, which equates to the number of condensation nodes that I've created at a rate of 1 per tooth. Okay, and then underneath each of those, I basically have each column here showing me the data for one full cycle of that electric motor. So in this case, it's one rotation of the rotor shaft. So what I'm going to do there, it doesn't matter what kind of resolution this data is, but obviously the more the better. I'm just going to select one of those and just very quickly show you what this equates to, just to give you some perspective. So you can see there that on one particular tooth, that's showing me how that load, the tangential load on that particular tooth, is varying over the entire period. And that will be a slightly phased result for each of these teeth. And this is the data we're going to import. It's very much the same with the radial loads. So again, we have a sheet of speeds, and then we have individual sheets that show stator teeth along the top. and loads for that particular stator tooth going vertically down. Okay, so to actually import this data is relatively simple. All we're essentially doing is telling MASTA where it needs to look in that Excel sheet for particular bits of information. So just bear with me for 1 second while I find the right folder. Okay, so you can see I've already got one set of data in here. We can put multiple in there. So I'm just going to make sure that I've got my Excel option selected, add the data set, and then it loads up this additional screen, which is, as I say, this one is just a visualization of the data that you've imported. So at the moment it is blank. The next thing I do is naturally need to select what type of torque ripple I'm inputting. So we've got a selection here. We can just do a constant torque if we wish, if we don't want to actually put torque ripple as part of our excitation. We can put in stator teeth tangential loads, which is what we're going to import in this case, which is the most complex, or we can just do the rotor torque ripple time series. So this is different ways of doing the torque ripple, and then we still have the ability to put in the radial loads and axial loads if need be. So in this case, I'm going to go with stator teeth tangential loads. Click on the add button here. That will load up an additional screen. And this is where we basically load in our Excel file and link up different points of data to different columns and different rows within the Excel sheet. So I'll do this very quickly as not to waste too much time. So stator tangential loads. And then I'm just going to link all of this up. So I'm going to read speeds from the Excel sheet, tell it on which sheet the speeds are occurring and how many speeds we have. Tell it which is the first row and column index. For the speeds, so in this case we are looking at column 1, row 2. Put our force units. And then critically we want to put in our first and last data points as well and the columns in which they occur. So it actually knows where it needs to start and finish reading this data. So very quickly, I want to start in column number 1, row number 2, and down to row 218. Okay, then if I've done all that right, when I click on Read Data, it basically opens up that Excel sheet, it reads all of the data that's in there, and will show you a plot of that along the bottom. So as I say, this is quite a simplistic example we've got here. Yours will be probably significantly more complicated than this, but it is showing that the data has been read in. And then if I click OK, it then shows us that in a different form and how that's going to contribute to the excitation of the different harmonics as well. So we've got our excitation at the top here. We've got how our torque varies over the period, which in this case is the rotation of the rotor. And then we do an FFT on that plot there. And in this case, we can see that our largest amplitude is harmonic 24, which is as we would expect as we've got 24 stator teeth. Okay, then we do have the option for force visualization as well. So this is the ability to actually view this on a polar plot as well. So if you actually wanted to see how these were varying, This is a very bad example of data to show you here because, as I say, it's very simplistic, but it would actually show us how that load is varying as it's going around as we go through the positioning period. Okay, so a few other bits of critical information here. So an important thing is the ability to actually cut off certain amplitudes. So if you leave it like this and you look in NVH mode at some excitations, as we'll do in a moment, you will basically see every single harmonic of that motor excitation on the NVH plot. Now this is fine, but it might be a little bit messy depending on your preference. You can put in some amplitude cutoffs for the harmonics. So anything below a particular value will not show on your NVH plot, and it will just make it a little bit tidier for you. It just makes it so it only shows things above a certain value of interest to you. Okay, we also have the ability to display the different types of data here as well. So for example, we've got the tooth tangential loads and the different speeds. And then we can show the interpolated data as well. So we have those particular speeds in which we've imported. So 1,000, 10,000, and 14,000 in this case. However, if we want to show what interpolated speeds we can get, we can do that as well. Okay, the importing of the radial loads is pretty much exactly the same. I'll leave it in this case just for the sake of time. However, the import process is pretty much the same. Okay, so for actually viewing this in NVH, first of all, we need to make sure that we're actually using this data as part of our load case. So I didn't import the full set there, as you saw, but I'm just going to revert back to this previous set of data I had imported. So the first thing I want to do is to go to one of my load cases. I have a pre-made one here called EV excitation load. However, the main property that you need to look for here in the main inputs of your particular load case, underneath the power loads option. So this is where you would normally import your speed, your torque, and your power. And by default, these are going to be set to constant torque. However, when you have your power load set to be an electric machine, by default, it will probably still show a constant torque in here. However, we do have the ability to change this to use any imported electric machine excitation data. So this is the data set that was imported. And then basically what I do here is I define an input speed at that particular electric motor, and then it will calculate the rest for me. Once we've done this, we go forward to our NVH mode. Find that particular load case. And then I'm just going to go to my editor to show you it would actually bring in and actually be able to show this excitation within the model. So this is a standard setup screen you will see for our NVH module. So critically, we have the number of modes, which is obviously quite important to set. We have the excitation from the cylindrical gears up here. However, if under our load cases we have that motor excitation selected, we now have a power loads option appearing as well. So you'll see we have the input power load. At the moment, the excitation type is set to none. However, I can switch this to be electric machine, speed dependent torque ripple, and radial loads. Okay, then we do have the ability to modify the data at this point as well, if we so wish, but this is the same screen that we saw earlier on. And basically, in terms of actually setting MASTA up to view motor excitation data, that's all you really need to do. So when I actually run this through, presuming I've not broken my model in some other way, so this might take a minute or so to run through, we'll actually be able to view the excitation data on any of the other plots within MASTA. So our dynamic response plot, our waterfall plots, our order cuts, will be able to show us the excitation from the electric motor. Okay, so that successfully ran through. Now if I just run forward to my dynamic response tab to actually show that motor excitation. Okay, so I'm just going to go and select a component. So I can see the excitation, as many of you will know from MVH mode, on numerous different points. I can either do it at a mounting point, such as a bearing, or maybe a rigid bond or something, or I can have a look at various points on the housing as well if I've set up some kind of accelerometer node. And this is something I'll show you a little later on. So if I, in this case, select a bearing, so maybe the one that's close to my electric motor to begin with, go to my dynamic response, that will load up a waterfall chart for us. And as you can see, in this case, I didn't actually cut off any of my amplitude harmonics. So it's basically showing me excitation from every single harmonic of that electric motor. Now you remember in the setup of this particular load case, I didn't include any gear excitation. So all we're going to see in this point is the electric motor. However, we can put as many or as few of these on as we want. So we could overlay excitations on top of one another if we wish to do so. Okay, so you can see, for example, if I hover over a particular order, it will show me what that is. So if I hover over this one, which is actually showing me an excitation, I can very clearly see that it's the 24th harmonic, order 24, which is what we would expect because of the 24 teeth. And then hypothetically, if I wanted to do a bit more analysis on these, just to very quickly show you. So let's say we were comparing this to acceleration, so we can view the results in a slightly different format. I could then overlay my coupled modes on top of this. So this will actually show us where the natural frequencies of the system are and how they interact with our excitations. So let's say, for example, I want to look at this one up here, or maybe quite high up a frequency of 4 kilohertz. Let me just turn up my frequency scale just so we can see a bit more of that simulation. So one of the things I want to note here is that I calculated 150 modes. However, at a frequency of about 4.4 kilohertz, we do actually run out of calculated modes, so we can't really trust anything that's happened beyond this. If you get in this situation, all you need to do is go back to that setup of your load case, up the number of modes it's calculating just by changing that one box, and rerun the simulation again. As you saw, it only takes a matter of seconds, so it's a very quick thing to do. Okay, so let's say I want to look at a particular mode shape here, and I'm looking at this particular excitation up here, and I want to look at this in more detail. So this is about 4 kilohertz. However, I can kind of see the modes that are involved. However, I might want to see this in a slightly different way. So I could go forward from my waterfall plots to my order cuts to take a look at this. I can then say, okay, well, I'm not too bothered about most of my excitations here, so I just want to look at my order 24 or 24th harmonic. So I could turn off the harmonics I don't want to see. In this case, the 24th harmonic is the one that's standing out, so it's not too difficult to observe. So I want to show coupled modes. I'm going to zoom in on the location of that peak. And I can see in this particular case that the peak in response is occurring at mode 117. So I might say, hypothetically, I wanted to go into my 3D view and have a look at what's happening at mode 117. So I go to my 3D view. I'm going to start off with my coupled modes. I'll get onto the other options in a moment. And go to mode 117. Okay, and then this will basically allow us to see what is being excited at that particular mode. Oops, excuse me. Right. So just looking at the mode model, or the node model, for example, I can see that there's some motion in some of these internal gear blanks, some of the internal shafts. Obviously, if that's not quite clear enough, we can view the model on there as well, so the components. So I could say I want to look at the actual shaft components, for example, to see how they are performing. I can see at this particular mode there does seem to be quite a bit happening, so there's some kind of mode shape of this gear blank occurring, this one as well. And we do see that we have a lot of motion in the excitation in the nodes for the stator teeth as well. If I wanted to take a better look at those, I could do so as well. So I turn on my solid FE. I can clip through the model to have a look at what's going on inside. And I can see in this case that we do have quite a lot of excitation at that particular frequency of the teeth themselves. Now this is a case where you might want to take those values with a pinch of salt, depending on how you've modeled this, as just remember that we are missing a lot of those internal components in there. Something worth keeping in mind. So this is looking at one particular coupled mode shape, but you might want to also look at you might want to know if there's some interaction with other similar frequency modes. So as well as just looking at individual mode shape actions, we can look at operating deflection shapes by excitation and operating deflection shapes by order as well. And this just allows us basically to select different parts of the waterfall plot and see like a combined effect of what's going on. So I could say, for example, operating deflection shaped by excitation. I can choose the excitation I want to look at. So let's go with my tangential load, harmonic 24. And then I would look at the particular speed which was of interest to me. So if I go to my dynamic response, okay. And then in my particular case, my peak in speed is occurring at around about 9,800 RPM. So maybe I could go into that. Okay, and that should show me, which this computer does seem to be struggling with, unfortunately, exactly what's happening at that particular excitation. Can also do deflection shapes by order. Which will again do the same thing. Okay, so the next thing I want to talk about is the adding a modification of flexible mounting points within MASTA. So this is something that we get a lot of now. And does seem to be particularly prevalent in EVs. So what we would classically do is basically just mount the actual FE component that we brought in. If I just find an appropriate model here. So there's a couple of examples in this model. And what we will classically do is when we're actually creating the FE component here, we would actually put some grounding points within the FE component. So you can see what the representation of the simple EV we've got here, some solid, rigid grounding points have been put in at various points on the model. So when we actually bring this within the MASTA interface, within the MASTA window, it basically knows that they're going to be grounded at those points, and it calculates around that particular piece of information. However, in many cases now, you don't want to consider those as solid mounting points. You might have some known flexibility in there. You might have some flexible bushings in there, for example, that make this not quite rigid and make this particular kind of simulation obsolete. So we do have a suggestion for how you would manage this within MASTA itself. And you can actually put in customizable mounting points. And this is basically through the introduction of rigid bonds at those particular mounting points. So this model has some of those to show you now. So you'll see at each of those points where we saw the grounding points a moment ago, in this particular case, we have a rigid bond component at those points. So a rigid bond component is, obviously it was designed classically for internal components within MASTA, so connecting things together. However, we can use them as mounting points. There's a couple of ways we can make them. One way is to actually make some condensation nodes manually on the casing at the places that you want the mounting points to be, and then positioning the rigid bonds at those particular points. Or alternatively, you can position the rigid bonds at the points beforehand and then just create the condensation nodes from that particular rigid bond. Each one has its own benefits. They don't really take more time than one another, and they're both relatively simple procedures. And because this is getting more common, we're looking at making this a little easier moving forward as well. So the reason we would actually include this, and I'll show you how to create those condensation nodes in a second. The reason we would actually do it this way is that these mounting points are now fully customizable in their stiffness. Now at the moment we have an individual stiffness value for each of these points, but you could, for example, connect those together with one mounting point in the middle, if that's more realistic for your model. This can be modeled in a multitude of different ways. But what I want to show you here, so if we look at one particular mounting stiffness, so if I select one particular component and look down in the properties list, you'll notice that we have some simple stiffness information down the bottom here. Now when you add a rigid bond into your model, by default it is going to be very stiff. The stiffness values are very high, however they are fully customizable. We'll also notice that we have the ability to switch the stiffness type. So by default there will be a simple stiffness, which just gives you the ability to directly modify a stiffness value for axial, radial, torsional and tilt stiffnesses. However, you could specify a stiffness matrix for a particular component if you have that available. Which has got hidden by another screen on my machine, so if you bear with me for 1 second. There we go. So this allows you to put in a 6x6 matrix of stiffness values. Alternatively, you can put in a non-linear stiffness as well. So change that to non-linear. I then get the option for each of the 6 degrees of freedom to put in a curve of stiffness, like so. Now, to do each of these individually would be a bit of a pain. So this is where it's quite good to utilize some of the custom reporting functionality. I'm not going to go through this in much detail, but just to show you the kind of thing you can do quite simply using this piece of functionality. So if I go on I've put all these mounting points here in their own assembly. And I've pre-made a report. So if I go to my editors, and a report I've created called mounting point stiffnesses, and you'll see what I've got here is a full list of all the mounting stiffnesses that I've got in my assembly here. And then in those, it's giving me positions, it's giving me angles, and associated stiffness values at the end as well. So instead of having to modify them all individually, I can just go through and copy and paste from an Excel sheet if that's an easier way to do it for you, or just manually enter values in this way rather than doing them one by one. So for example, I could select all of those values there and modify them all at the same time. Okay, so another couple of things to show you. These are just minor modeling things that are worth keeping in mind. The first one is the ability to model additional rotating masses. So I've got pretty much a complete version of a model here. However, in order to get an accurate correlation between our test bench data and our master model, you may need to put in some additional rotating masses that aren't actually a critical part of your or functional bits of your transmission. So an example of this might be if you've got some parts of a synchronizer in your particular model, or if you've got some a park lock in there and there's a wheel which will be rotating on there or would be sitting on one of your shafts. It's additional mass and some slight additional stiffness which you might need to model in order to get the correct natural frequencies of the system. So the way in which you would do this is just to add, or ideally if you could do it as an FE component, that would be ideal, as then you're getting the exact correct influence of that particular component. However, if you want to keep it a little bit more of a simplistic approach, I can just add in a component to our master model, which is the mass disk. That gets added in as this pink component down here, which you can just connect as we would with any other component. And then with this selected, if we look down to our property list here, we get the ability to import various different properties onto here to actually model any additional mass into our model. So for example, the density of the component, or you could directly import the mass, outer diameter, polar inertias. Whichever way you prefer to enter this information, you can do so in this method. Okay, and the other thing I want to show you is the modeling of upstream and downstream inertias. So I briefly mentioned this earlier on in terms of the electric motor power load. So when we've got the actual electric machine power load type selected, it's not too much of an issue because MASTA recognizes that this is the rotor and there's not going to be an upstream inertia. However, if we're looking at the lower side of the model here, so where it goes out to the wheels, for example, chances are there's some point where we're going to have to cut off our master model. We're not going to be able to model the entire rotating inertia as accurately as we may want. We may have to cut the model off to keep it a reasonable size. So in this case, the model's been cut off at the half shafts. In reality, of course, there would be some wheels on the end of here and obviously some more half shaft. And if I click on my two output power loads, so the ones I've got on my half shaft here, you will notice in the properties list there is an upstream and downstream inertia properties. Now this is a simple value you put in, which does allow you to just simulate that downstream properties and will allow you to get, or hopefully get you a bit more of a realistic correlation. So it's all these little bits of modeling detail that you could put in there just to help you towards getting an accurate model in comparison to your test data. Okay, so I want to spend the last few minutes talking about part locks. So this will be quite brief, but we've had a few questions recently talking about how we might actually model these particular types of components, how we would simulate if the part lock is on, how might we simulate that particular condition. And we can do so within the software itself. However, it is a bit of a different way of modeling than you would expect with something like this, for example. And in order to actually demonstrate this, I have a very simple model that we've thrown together of basically just a representative part lock. So there's no gears or anything in the system. It's a very simple example model. Basically what we're having here is a very simple simulated housing with some grounding points. We have our part lock arm, which is part of our housing FE in this case, but could be brought in as an individual part of an FE. And we have our wheel, which is then connected to our otherwise rotating components. Okay, so one of the main things we need to point out when you're doing this kind of modeling is that in this particular case, both the wheel and the housing that we've brought in are considered to be casing components, even though obviously they're not. The reason for this is that if we had this as a replaced shaft, if we had the wheel as a replaced shaft, for example, we wouldn't be able to connect a bearing to it. So in this case, we have the connection simulated by a clearance bearing or a concept bearing. However, if we were to use a rotating shaft for this component, we wouldn't be able to connect the bearing to that rotating shaft in this sense. So just to show you that in a little more detail, so in my FE mode, one of my components is my housing and arm. So I've done this as one component just for an example's sake. However, you could bring this in as separate FE components if you wished. However, the setup would be a little bit more complicated. Then I also have my parking lock wheel as well, which again, just to reiterate, is brought in as a housing component. And then when you bring this in, you do still connect it to a rigid bond on the inside here, which is then connected to the rotating components of your master model. So what this basically allows you to do is ground all of those together. So when we try and put a torque through our input load now, it is going to try and put that torque through the housing there, through that park lock ring, and then it's going to transfer that load through this contacting node here into the arm. So this is done, as I say, in quite a unique way. So we have our housing, our actual housing component here, and then we've created a couple of nodes. So there's one node being created on the outside of the arm here. And this is very simply done. So with our housing and arm FE selected, I'm just going to demonstrate this maybe a bit further up the arm just to show you how it's done. I can go to my condensation node tab along the bottom, and then we have this section on the right hand side here which is allowing us to actually create a node, create a condensation node anywhere on our particular selected FE component. So I want to make this a bit more visual, so I could put on my mesh. And then over on the top right, where I have my selection of different aspects of our FE component, I'm going to switch from component to face. And this basically allows me to actually select different elements within the model here and actually put a condensation node at that particular point. So I could say, for example, I want to select these 4 elements here, or whatever my contact region may be. And then I can click on create, and it will make me a condensation node at that particular point, which is connected to all of the FE nodes associated with those elements I selected. Okay. And then basically what we would do on the other half is to do the same thing again. So we create a node, make sure that they're exactly the same coordinates, and then we basically position a clearance bearing, or a bearing which is most applicable to your setup of your master model at that particular point, and then that is simulating the connection between the two component types. So what we've essentially got here is, as the torque is going to be passed through this particular power load, it's going to try and torque up that shaft, which is not going to be able to move because it's grounded. It's going to push against this clearance bearing here, which has defined stiffness properties, and transfer the load over into this arm and into the housing. So obviously, set up like this, you won't actually be able to run your model in a normal condition. So this particular setup is going to ground your model. So if you try and run one of your normal load cases, it's not going to be able to do so. You'll get some failure or just not working as you expect. So this would have to be kind of an additional setup, which you'd have stored somewhere else. So if I just show some results of this, hopefully I've not messed up my model by putting that extra node in there. It should still run. If I go to System Deflection and run through my load case, and then within the 3D view, I can actually show how that whole system is reacting to that particular setup. So I can say, for example, I want to view the FE. And I can show deflections. Obviously, it's an exaggerated deflection, but it's showing me how that particular system is reacting to that setup. I can also show some contouring on here as well. So if I wanted to get some indication as to how much my casing was deforming, how much my arm was deforming here, I could put on contouring of displacement. Or I could even calculate the stresses on the component as well. So it's worth keeping in mind when you're calculating the stresses that the mesh that you would normally use for stiffness matrices such as these probably aren't fine enough for an accurate stress calculation, but they will at least give you an impression of what's going on. Okay, so I can see where the stresses are occurring in that particular model. Okay, so if anyone is trying to model this particular setup, feel free to fire us an email or request it from me at the end here. This is not a confidential model, as we've seen. It's a very simple example. We can share this with you if you want some kind of reference point as to how we would model this. You can use this as a reference. Okay, so in terms of the actual agenda I have, that is about it. There are a couple of questions that have come in. Just read through those here. Give me 1 second. Okay, so I think another question I've got here is asking to just re-clarify what the data was in the Excel sheets that I showed. So going back to my tangential loads in this case, just to clarify again what I meant here. So my stator teeth are shown along the rows, and the first row is showing my stator IDs, my teeth IDs. And then going down, each of the columns is the loads on the particular teeth. So I have a load on the teeth at various points along the period. So in this case, it's a full rotation of the rotor shaft, and this is basically showing us how that load on the rotor shaft or how the load at a particular tooth varies as the rotor shaft rotates. Okay, and then the last question I've got here is, can MASTA interpolate between speeds during the MVH response calculation? Yes, hopefully that's been answered during the webinar. I think I might have answered that after you asked the question, but just to reiterate, yes, we import the sheets here with a defined number of speeds. As we see, it's impossible to bring in every single speed. However, MASTA will interpolate between those. So if you specify a particular speed in your load case, it will interpolate between those sheets to actually get you a particular loading. Okay, so the last thing I want to point out here is just our next webinar. So that is the end of the technical content. Hopefully you found it useful. Our next webinar, which you can sign up for now, in about 1 month time, is going to be hosted by my colleague Matt, and it's going to be talking about system deflection analysis in more detail. So we've covered it very, very briefly in this particular webinar where we're looking at our part lock. So you've seen some of the capabilities in the 3D view and that kind of thing. The next webinar will be going into a lot more detail with system deflection analysis, and you can sign up to that now. If you've got any additional questions on EV modeling or analysis, I will stay on the webinar for a few extra minutes in case any extra questions come in, and I will answer them by text in the background. Apart from that, thank you very, very much for attending. I hope you found it useful, and we hope to see you again at the next webinar within our series.